All right, let's dive right into this explainer. We interact with digital interfaces pretty much constantly, right? But honestly, how often do we actually stop to think about the literal microscopic mathematical gymnastics happening right beneath our fingertips? Today, we're going to discover exactly how computers, which, remember, at their absolute core only understand simple ones and zeros, somehow manage to store and process the incredibly complex, real-world data that we rely on every single day. To get us there, here is our roadmap for decoding the machine. First, we'll look inside computer memory. 2, we'll tackle the Endianness puzzle. 3, real numbers and binary. 4, the IEEE 754 standard. 5, a step-by-step conversion. And finally, number 6, encoding characters. Let's get into it. Kicking things off with Section 1, inside computer memory. This is really about where the data actually physically lives. So literally every single piece of information your computer processes starts right here, inside a memory cell. You can kind of think of a memory cell as a tiny physical mailbox. And just like a real mailbox out on the street, it has a highly specific address, so the system knows exactly where to find it. Now, each one of these little mailboxes typically holds exactly 1 byte of data, and that byte is made up of 8 individual bits, those basic ones and zeros. But here's the catch. What happens when the data we want to store is just way too big to fit inside one of those single byte mailboxes? Well, that brings us to Section 2, the Endianness puzzle. Endianness is the brilliant solution to that exact puzzle. When you have a massive chunk of data, let's say a 32-bit 4-byte sequence like the hex value E2564F52, it literally has to span across 4 distinct memory cells. So the computer basically has to make a choice, right? It must decide the order in which to pack those bytes into memory. If it takes the most significant byte, which is the leftmost part of our data, and stores it at the lowest memory address, we call that Big Endian. But if it flips that logic, grabs the least significant byte from the far right side, and stores that at the lowest address first, well, that's Little Endian. It's essentially just the computer deciding whether it wants to read a multi-byte word from left to right or right to left. All right, moving right along to Section 3, real numbers and binary. Let's see how all this builds up when we throw decimals and fractions into the mix. Okay, so standard integers are relatively straightforward. But to handle the massive, infinite universe of rational and irrational numbers, like 2.5 or 123.456, computers have to use what's called a floating point representation. And this entire system relies strictly on good old scientific notation to encode numbers. It doesn't matter if we're dealing with standard base 10 decimals or base 2 binary, scientific notation always gives us 2 main puzzle pieces, a mantissa, which represents all the significant digits, and an exponent, which tells us exactly where that decimal point needs to float. So the real magic is how engineers managed to standardize this crazy translation globally, which brings us to the absolute hero of our story. Section 4, the IEEE 754 standard. The way this standard breaks everything down is just incredibly elegant. If we're using 32-bit single precision, IEEE 754 slices those 32 bits up perfectly. You get exactly 1 bit for the sign, 8 bits completely dedicated to the exponent, and the remaining 23 bits strictly locked in for the mantissa. Let's clearly define what each of those 3 blocks is actually doing under the hood to capture a real number. First up, the sign bit. It is incredibly simple. A 0 means the number is positive, and a 1 means it's negative. Next, the exponent field. Now this has to handle both positive and negative exponents, so engineers came up with a really clever trick called a bias. They literally just add a set bias, which is 127 for single precision or 1023 for double precision, to the actual exponent to get the stored exponent. Finally, the mantissa holds all your significant digits, and it is normalized, which basically just means we format it so there is exactly 1 1 sitting just to the left of the decimal point. Okay, I know that sounds like a whole lot of abstract rules, so let's actually get our hands dirty and put this into practice. Section 5, step-by-step conversion from decimal to binary. We can mathematically chunk this whole process by converting the integer and fractional parts completely separately. Let's take the number 85.125. First, the whole number, 85, becomes the binary sequence 1010101. Then, for that 0.125 fractional part, we repeatedly multiply by 2. We get a 0, another 0, and finally a 1, giving us 0.001. When we smash them together, we get 1010101.001. But wait, remember? We need scientific notation. So we simply shift that decimal point 6 places to the left to normalize it, which leaves us with 1.01010101 times 2 to the power of 6. From that absolutely beautiful scientific notation equation we just built, we can now cleanly extract our 3 key ingredients for the IEEE standard. Since our original number was positive, our sign bit is just 0. Our actual mathematical exponent is 6, and the mantissa, which are those crucial digits trailing right after the decimal point, is 0.101010001. Next up, we need to calculate the stored exponent. We take our actual exponent, which is 6, and simply add it to our required bias. If we want 32-bit single precision, that bias is 127. Add 6 to that, and boom, we get 133, which in binary translates to 1000101. Now, if we were building out a massive 64-bit double precision number instead, we'd add 6 to 1023, giving us 1029. And there it is. Let's put all the puzzle pieces together for a single precision standard. We've got our sign bit of 0 right at the front. Next, our 8-bit stored exponent of 1000011. And finally, our mantissa, which we pad out with extra zeros on the right-hand side to perfectly fill its 23-bit slot. The decimal 85.125 has been translated entirely into a pristine 32-bit sequence of ones and zeros, perfectly ready to be slotted into a computer's memory cells. Now, just to appreciate the sheer scale of modern computing precision, think about this. This massive string of ones and zeros is what that exact same number, 85.125, looks like when expanded to 64-bit double precision memory. I mean, just look at the length of that padded mantissa. It truly highlights just how much space we literally allocate to guarantee absolute decimal accuracy in our complex software. All right, we've thoroughly conquered math and numbers. But what about the text you're reading right now? That brings us to our final stop, Section 6, Encoding Characters, from binary to text. To wrap things up, it's absolutely crucial to realize that literally everything processed by a computer is fundamentally just binary sequences. So for your computer to communicate using text, every single letter, every space, every punctuation mark requires its very own dedicated binary sequence. To keep the digital world turning, we rely on entirely different but equally vital encoding standards like ASCII code and Unicode to consistently map these specific characters to specific bytes. It really leaves you wondering, doesn't it, when you pull back the curtain and see the intense, rigorous logic required just to store a simple decimal number or a single letter in memory. It reveals how fragile yet mathematically beautiful the foundation of all our modern digital infrastructure truly is. Without these invisible global standards working tirelessly to translate our physical reality into microscopic ones and zeros, would our entire digital world just instantly collapse?